Okay, today we're going to talk about the power rule of the derivative, which is a really important rule that ends up being kind of the foundation for a lot of the other derivatives that we do. And the rule can be summed up here. If we have an f of x that is x to the n, where n is a constant and x is a variable, well, then we're going to move the n to the front. In other words, multiply that particular term by that n, and then reduce the power by 1. If you're interested in seeing a derivation for this, we'll produce that in a separate video. But for now, let's just talk about the functionality of this rule. So let's say we have something like f of x equals x to the third. We can conclusively say that the derivative of this would be, we would move this 3 to the front and multiply by said 3, and then reduce the power here by 1 from 3 to 2. So the derivative of x cubed is 3x squared. Let's try a few examples because this rule really is best demonstrated through the use of examples. The first one here we have f of x is 7x squared plus 6x cubed minus x to the fifth plus 10. So why don't we go ahead and work through term by term. I'm going to multiply the 2, let's use a different color here. Multiply the 2 to the front here. We're going to get 14, and then we're going to reduce the exponent from 2 to 1, so we get 14x. Same thing happens here. I'm going to multiply the 6 by the 3. It's going to produce an 18x, and again I'm going to reduce the power by 1 and give me 18x squared. Here, move the 5 to the front, keep the negative, nothing about that has changed, so multiply by the power and get 5x, and again reduce the power by 1 to the fourth. Now this last one here is a bit of an interesting case. We have a 10, which is just a constant, and the derivative of any constant is always 0. We can think about that visually. If we have, let's say, f of x equals 7, and we do a very quick sketch of that. Remember, the derivative is defined as the slope, and the slope at any point on this line is precisely 0, no matter how high or how low the line is. So then this term actually ends up being irrelevant. So one property that does give us is that the constant doesn't actually matter a heck of a lot in terms of the derivative. In other words, if I replace this 10 with a 5, or a negative 5, or even something completely ridiculous like negative 753.24 times pi, that's still a constant, and it's still going to end up having its derivative as 0. So let's check out the next question here. Here we've concluded that the derivative of 7x squared plus 6x cubed minus x to the fifth plus 10 is 14x plus 18x squared minus 5x to the fourth. Now let's examine the next one. I gave you the g of t function. And again, of course, the variable nor the name of the function, neither one of those things really matters. So rule is exactly the same. Multiply the negative 2 to the front of this term and get negative 6. And again, we're going to reduce power by 1. So it'll be t, well, what's 1 less than negative 2? It will be negative 3. Next term, we're going to move the 5 here and reduce by 1 and produce a 10, 2 times 5, t to the fourth. And then lastly, we have t squared. We're going to take the 2, multiply that term by that constant, and it'll be t to the 1, which we don't need to show the 1. And we got one more on this page, and then we're going to have a couple that are a little bit more difficult. Here I've got x to the 1/2 minus 7x minus 2x to the 4th. Nothing changes, just some of the math becomes a little bit trickier. So here, I'm going to take this 1/2, move it to the front. And then to get this term up here, I need to get 1/2 minus 1. You may either intuitively know that 1/2 minus 1 is negative 1/2, or you could perform a couple of basic steps here. Change the 1 to 2/2, and then simply subtract the numerators now that we have a common denominator. So in here we've got a negative 1/2. And in here, minus 7x. Okay, so this is technically speaking x to the 1. So let's say we have a term to the 1. Let's call it g of x, some hypothetical g of x that's just c, the constant, times x. Again, c being the constant, x being the variable. Well, this is going to be implicitly x to the 1. So if we move the 1 here, we're going to multiply this by 1, so we're going to get 1c, and then we're going to reduce this, which is x to the 0. Now we know that anything to the 0 power is 1. So we are left with just c. So a simple rule is if we have a g of x, or f of x, is equivalent to cx, or any term of it is, then the derivative of that particular term is always just going to be c. Okay, so the derivative of 7x then is just 7, and then here we're going to move the 4 to the front here, multiply by the 2, and get an 8x to the 3rd, and that'll be it. And then we could tweak the formatting a little bit. For instance, we could certainly use the negative exponent properties up here to just move that into the denominator. And you can even change that to a square root if you'd like, which we're going to tinker with a little bit more on the next page. Okay. So let's take a look at a couple of more complicated derivatives. We've got a few more fractions here. We've got some variables under radicals. We've got a few fractional and denominator variables as well. So let's look at the first one here. We've got 3x squared plus 6x minus 1/5 x to the 5 plus 18. This looks to be a fairly straightforward one, so we're just going to go ahead and multiply each term by its power. So here we're going to have f prime of x, and make it a little bit thicker. It's going to be equal to 6x to the 1 plus, well, here we had that x to the 1, right? That was from the rule we learned before. That's 6. Now here we're going to multiply the 5 by the 1/5. 5 times 1/5 is 1. So we've got minus 5 times 1/5 x to the 4th, because again we're going to reduce that power by 1, and then here we have the constant. We can disregard the constant. And again, I'm just going to go ahead and simplify this. Just reduce to 1. And my final answer here is going to be f prime of x is equivalent to 6x plus 6 minus x to the 4th power. Okay, let's have a look at the g of t here. Let's consider what we're going to do with the g prime of t. Now, we've got a couple of situations here that we hadn't looked at before, the first of which is this. We have the square root of t, which obviously is not immediately a power. Now, of course, we should remember that we can convert any radical into a fractional exponent by using the following rule. If we have x, and here we have an a, and here we have a b, where there's an implied 2 here, This is a square root. We don't have to put that. Sometimes there may be an index here, which would indicate a cube root or a fourth root. Well, we could rewrite this as x to the a over b. So I could rewrite this here as t to the 1/2. Okay. And then here I should also have a look at this term where I've got an exponent in the bottom, in the denominator. And again, we should remember a property from algebra where we have here 3 over t squared. I can rewrite this as 3 times 1 over t squared. And we should remember that if we have an exponent in the denominator, we can just simply make that a negative exponent in the numerator. So this is equivalent to 3t to the negative 2. And again, the rule here just like here, we had this rule to relate to the first term of the second question. Here we're going to have this rule to relate to the second term of the second question. Well, the rule is going to be if we have x to the negative a, it's equivalent to 1 over x to the positive a. That's a useful rule. So again, I'm going to go ahead and rewrite this as 3t to the negative 2. And certainly it would help to stay organized here. So I'm going to go ahead and rewrite this entire thing. And optimally, of course, you're going to want it in this format every single time. Just a simple addition, subtraction, combination of terms with exponents. So let's otherwise follow the same exact process we had before. We've got 1/2 t, and from an earlier calculation, you should know that 1/2 minus 1 is negative 1/2. And in here, we're going to multiply the negative 2 by the 3. We get minus 6t to the negative 3rd. And then here, we're going to multiply the 3 by the 6, and we get here minus 18, because we do have a minus here, t squared. Now, certainly, you can go ahead and simplify this final answer. G prime of t would be 1 over 2 t to the 1/2, or square root of t, minus 6 over t cubed minus 18t squared. Excuse me for the very inefficient use of space here. Okay. And I'm actually going to go ahead and transpose this last question to the next page. Just so we have a little bit more room to work with. Okay, and the first thing I'm going to do is rewrite what needs to be rewritten. Now, the first term is already given to us, which is nice. The second term is going to be 7x to the negative 3. And then the third term is going to be 2/3. We can always take a constant out. And then this is going to be x to the 1/3 in the denominator. So then I can actually rewrite this one more time as 2/3 x to the negative 1/3. So don't forget the step here. Don't forget the step, rather, just you don't have to show it once you become familiar with these numbers. So here we're going to go ahead and do h prime of x. First things first, multiply by that, and the 2/9 goes to the front. We got 2/9 x, and then here we have to calculate our new power, which is going to be 2/9 minus 1. And well, that's 2/9 minus 1, which is 2/9 minus 9 over 9. That's the equivalent of 1. And we get negative 7/9. If you choose to work with decimals, it would work, but you'd end up with a few infinite decimals. You really don't want to do that. It becomes very messy later on. Here again, multiply the negative 7 from here by the negative 3, so plus 21x, and again I'm going to reduce the power to the negative 4th. And lastly, 2/3 that's going to be multiplied by -1/3, okay, by virtue of this multiplication. And then x, now let's consider what happens to this -1/3 here. I'm going to have to do -1/3 minus 1, which is -1/3 minus 3/3, which is -4/3. So here we have x to the -4/3. I'm just going to go ahead and simplify some of this algebraically. And that's about it. Thank you for watching.